Here's another problem that we're going to use the work energy theorem to kind of help us out in terms of the dynamics. So I've got an automobile that weighs 4,000 pounds. It's being driven down a 5% incline at 60 miles an hour when the brakes are applied. The total braking force is 1,500 pounds, and we want to determine the stopping distance. So as we have my usual artistic ability here, I've got a car. We're going to try to determine the stopping distance along our incline plane. We know it's a 5% incline, and we're told that the total braking force is 1,500 pounds. That's going to be the friction plus the brakes and all of that, but we don't necessarily have to calculate it out. So we're going to use our work as a change in kinetic energy theorem, and we're going to also utilize our forces. Now remember, because we can change our coordinate system here, we can use the forces that are parallel and the forces that are perpendicular. So my parallel forces are going to be the force down the inclined plane and our braking distance, our braking force of 1,500 pounds. Now I am making the assumption that I'm going to use this along the parallel as positive, go in this direction as positive, and having my braking force being negative. And we know that the perpendicular force is associated with the weight of the car, 4,000 pounds times the cosine of 5 degrees. Now, because we're dealing in pounds, we want to make sure we're in feet per second. So the problem gave it to us in miles per hour. So we're going to have to convert into that feet per second. So I messed up, did a little bit of conversion there, and we show that the velocity of the car at 60 miles an hour is really about 88 feet per second. Now I know all of us probably jumped right to that 27. Remember, that's meters per second, not feet per second. And if you think about multiplying 27 times 3, that's going to give you over 75. So this number is definitely reasonable. So that does make sure that we've had that reasonable number, because we're not necessarily as familiar with working in feet per second, just like we weren't familiar with working in meters per second. So my change in kinetic energy is 1/2 the mass. So I've got to account for the fact that I was given the weight. I wasn't given mass. And I know that that is going to have to divide by my acceleration due to gravity in feet per second squared. We plug in our velocity. And so my change in kinetic energy is going to be 481,000 foot-pounds. Remember, when we're dealing with energy in the English system, we're dealing with foot-pounds. So now we're just going to go ahead and solve for our change. So here's our force. Remember, we're going to use the work that's going to be my force times my distance along the direction of the path. And S is the path. My braking force is 1,500 pounds along the direction of the path. And we already know what our change in kinetic energy is. So that's where my 481,000 comes into play. I go ahead and solve, and I'm going to solve that the braking distance is going to be 418 feet.